Hello class, this is Mr. Hart, and in this podcast we want to do the lesson on magnetic fields. And so last time you did a lab that kind of introduced you to how magnetic fields are measured and how we tell their direction. Okay, but in this lesson we want to be able to actually draw magnetic fields and calculate their strengths and things like that. So let's just look at a very basic example. Okay, in the lab you had a north and south pole, just standard bar magnet that you measured the field strength of, okay, and the direction of it. And what you hopefully saw is that on the outside of the magnet, the field kind of points in this direction towards the South Pole. Okay, so if you put a compass in there, it would point towards the South Pole, which makes sense, right? If it's a north-facing compass, it would go that direction. Okay, and towards the edges of the magnetic field kind of just shoots out on the north side like this, and then it comes in on the south side like this. Okay. And so if you think about a trajectory, right, the kind of the path that a magnet would take, okay, it's kind of weird to think of it that way, but it's how we visualize it. If you put kind of a north magnetic field pole on this side, okay, its trajectory would look something like this. It'd get pushed out from this north pole, right, and then it slowly would be attracted to the south pole and then come to this side, okay. And you'd see that on any side that you did it, okay. And so when we draw magnetic fields, okay, rather than drawing those white arrows, okay, like we would do with electric charge, we actually draw the trajectories, okay. It's kind of weird to do that, but it kind of helps us visualize the flow of the field much more than the individual locations, okay. And so if we redo this, rather than drawing those individual arrows each time, you'll see people draw magnetic fields just with the trajectories by themselves, okay? Just kind of showing that the magnetic field kind of goes around the outside of the bar magnet, okay? And if you kind of extrapolate this information, what you'll find is with magnetic fields, we have this key principle that we have to hold to, and that is that the magnetic field, okay, always flows from north poles to south poles, okay? When we're doing the drawings, those arrows that we draw, those trajectory arrows, always better start at a north pole and always better end at a south pole, okay? That's how you can know if you did it right, basically, okay? So if we look at this example where we have two bar magnets sitting next to each other, okay? Well, if we look at this north pole right here, its closest south pole is this guy. So anything that starts near this north pole will end at that south pole. Okay, and then if you look at this north pole out here, he doesn't have a south pole he's close to. Some of the really close ones might end up at this south pole, okay? But overall, most of the trajectories will end up at this south pole over here, okay? And like this, okay? And so if you kind of think about it, it's basically a big bar magnet, right? You can think of this as just being one bar magnet, okay? Let me undo that. Let's do that in yellow to separate. So you can kind of think of it as just one big bar magnet, basically, okay, with a north and south pole, okay? And so we can kind of see how things would behave, right? We get these multiple trajectories going around the outside, okay, just as if it was a huge bar magnet, right? And there we go, which makes sense, right? If we connected these two, it would be one big, huge bar magnet, right? It behaves the exact same way, okay? And so that's magnetic field lines, okay? And as you can see, it's not a nice, simple distance calculation like we had with electric fields, right? This field strength is going to vary tremendously depending on location, unlike with electric charges. It's pretty easy to just use inverse square law, okay? And so when we're trying to describe the strength of a magnetic field, it's not so easy to do, okay? But let's look at the calculation, okay? In this class, we won't calculate directly magnetic field strength, okay? Meaning if I have a bar magnet, what's its field strength? That's a really hard calculus problem that you would have to do. We're not going to do this for this class. But we are going to look at how that field can affect other things, okay? Specifically like moving charge, right? Because we said that a magnetic field is caused by moving charge, so it also can affect moving charge. Okay, so here's the calculation we're going to use for this class, okay? And it basically says that the magnetic force, or force magnetic, right, on any charge is equal to the amount of charge you have, okay? And then here's a cool part. It's dependent on the velocity of that charge, okay? Because, again, that charge has to be moving. So if it's not moving, the magnetic field doesn't affect it, okay? And then big B is a letter we use to describe magnetic field strength, okay? Or basically the strength of a magnet. You can think of it that way, okay? So this is a kind of an interesting calculation because it's dependent on the velocity of the charge, right? So you have some magnetic field that a charge is traveling through. If it's traveling through it at a certain velocity, there's a certain force that the charge is going to feel, okay? And so this is our equation, okay? And before we get into an example problem, let's talk about this magnetic field strength, big B, okay? So when we describe magnetic field strength, we measure it in what's known as Teslas, okay? So a 1 Tesla field is a way we could describe how strong a magnet is. But keep in mind, okay, just like 1 Coulomb was way too big, 1 Tesla is way too big by far, okay? A 5 Tesla field is enough to pull the iron out of your blood, okay? Like that scene in X-Men 2 where Magneto pulls the iron out of that one guy's veins and stuff, okay? That's a huge magnetic field. You won't see anything that's 1 Tesla in your lifetime, or if you do, you probably will die from it, okay? The world's most powerful man-made magnet is only 45 Teslas, okay? So these are huge fields. So most of the things we're going to be working with are like micro Teslas, milliteslas, okay, when we're talking about magnetic field strength, okay? So just keep that in mind. That big B, okay, it's measured in Teslas, but usually you'll see milliteslas on your problems, okay? All right, so let's try an example problem now, okay? So a particle with a 1 Coulomb charge is going through a magnetic field with a strength of 5 milliteslas. If the particle is traveling at 20 meters per second, what is the force on the particle? Okay. So let's start by identifying what we know. So this is our charge Q. This is our field strength, big B, and this is our velocity. Okay. So before we start, let's put big B into Teslas. So big B is 5 milliteslas, or that is equivalent to 0.005 Teslas. Okay. Then to find the force on the particle, it's very simple. You just say the force magnetic equals QVB. Okay. I guess that should be a lowercase v. So Q times V times B. So that is, the charge is 1 Coulomb. The velocity is 20 meters per second. And the field strength is 0.005 Teslas. So when you put that in on your calculator, you get that the total force on the charge is 0.1 newtons. Okay? And there we go. So again, keep in mind, this is a lot weaker of an interaction than the electric force was, right? If you have a 1 Coulomb charge and another 1 Coulomb charge, it's a huge amount of force, okay? And you have this 1 Coulomb charge that's going 20 meters per second through this field, it only feels 0.1 Newton. So the interaction between charges and the magnetic field is pretty weak when you think about it, okay? But there you go. There's our answer, is a 0.1 Newton charge, okay? Or 0.1 Newton force, excuse me. All right, so there we go. But before we move on from this problem, I want you to think about what direction will this charge feel its force. Okay, so let's say there's like a magnetic field going this direction, okay? And in the problem, the charge is going 20 meters per second. So here's our 1 Coulomb charge. It's going 20 meters per second this way, okay? It goes through this field. What direction does it feel the force? Does it feel to the right, does it feel it going up, left, down? Like, which way is it going to be accelerating? Okay. And so here's the weird thing about magnetic field problems is you have to do them in 3D. In this problem, if this was the setup, the charge would actually be moving into the page, I believe, if we think about it. Okay. It'd be moving into the paper, right? So we have to be able to think about it in 3D. Okay. And in order to do this, we would use what's called the right-hand rule. Okay, so this is the right-hand rule. Okay, because we're doing problems in 3D, it's hard to be able to describe what's going on, so we use the right-hand rule to figure out what direction the magnet's going. And it basically says, if the current or electric flow is going in this direction, you use your middle finger to represent that. The magnetic field is the direction of your index finger, and the force is going up. Okay, so let's see if I can do this on the screen properly. So if the in the last problem, right, we had that the particle was moving down, right? The charge is moving down, and the field was to the right. Okay, so if we're trying to represent that with the right-hand rule, we put our middle finger down, okay, with our right hand, okay, like this, because that's the direction of the electron flowing, okay, like it is right here on the screen. The magnetic field's moving to the right, okay, so you put your index finger to the right, and so the force, if you look at your thumb, you can kind of see my thumb, right, it's pointing towards me, okay, which means in the problem, the force would be going into the paper, right, or into the board, as we say. So it's kind of hard to visualize in 3D. I'll do my best. You can kind of imagine going into the board. Okay, so it's kind of hard to draw this in 3D. So what a lot of people will do is instead of drawing arrows, is they will do X's and O's, okay, basically. So in physics notation, a O means out of the board, and an X means into the board. Okay, so in this case, this would be the force would be X into the board. Okay, so it'd be pointing, basically the force would push it into the board in this problem. All right, let's try one more problem to make sure we have this down. Okay, so let's say this time the field is going into the board, so we'll represent it with X's, right? The magnetic field goes into the board. Okay, so we let's say we have a charge on the outside that goes to the left like this. Now we want to calculate what direction the force is going to push it, okay, or push the charge. So I'll use my left hand in this case just because of the way the camera works. But first of all, it's going into the board, so you'll take your magnetic field, your index finger, and point it into the board like that. The electric current or electric flows to the left, okay? So what that means is that the magnetic field will go up, or the magnetic force will push up. Okay, so what that means is this charge is going to feel a force in this direction when it goes through that field. Okay. Questions on that? So there's our right-hand rule. Okay. So that's how it works. Be careful with this when you're doing it. Okay, especially if the electric current goes up. Okay. Don't want to flip anyone off or anything like that. So just be careful how you're doing it. Okay. But that's the right-hand rule. Okay. Let's talk more about representing these fields into the board and outside the board or out of the board. Okay. So again, if you're going into the board, it's an X like this. Okay. Kind of representing that direction this way that we can't represent very well on paper. And then O's means out of the board. Okay. And sometimes they have dots in the center, but basically X's and O's. Okay. And the way I like to think about it is I often visualize like an arrow, okay? If you took like a bow and arrow and you shot it. So if the arrow is flying away from you, what you would visualize or see is kind of the feather tips on the edge of the arrow. And then if it's going towards you, if the arrow is shooting towards you, okay, you're seeing that rounded edge of the arrow, okay, kind of the tip with the circle and the dot, right? So however you want to visualize it, but just remember X means into the board, O means out of the board. Okay? All right, let's look at a couple more calculations. Okay? Another calculation for magnetic force is specifically on a wire, okay, that has a current going through it. So if there's a wire with electricity in a magnetic field, that wire can actually move. Okay? And it's kind of the same equation. So the force magnetic or magnetic force equals the distance or the kind of the length of the wire, okay, that's in the magnetic field. I is the current on the wire, and then again B is the field strength or magnet strength. Okay, so field strength. Okay, and so this kind of makes sense, right? If you think about charge times velocity for a wire, it's basically the length of the wire times its flow of electricity. Okay, so it's very similar, but this is how we can calculate the magnetic force on a wire. So magnetic force equals length of the wire in the field times the current on the wire times the field strength. Okay? Alrighty, so let's try a quick problem just to see if we got this down. Okay, so let's say a 10 centimeter section of wire is going through a 12 millitesla magnetic field. If the wire has a current of 16 milliamps, what is the force on the wire? Okay. So before we start this problem, let's put all these into SI units because there's a lot of conversions we need to do. So we say, okay, so the 10 centimeter section, that's the length or distance, right, D. So instead of being 10 centimeters, that's 0.1 meters, right? 12 milliteslas is the field strength. So that instead of being 12 milliteslas, that's 0.012 teslas. And then the current is I. And so instead of 16 milliamps, it's 0.016 amps. Okay. So now all we do is say the magnetic force is basically all those times together, D times I times B. So I say that's 0.1 times 0.012 times 0.016 amps. Okay. We're not going to worry about units for right now. It gives you newtons just like the other one did, so we're not going to be too worried about that. But we times those out on our calculator. 0.1 times 0.012 times 0.016. Okay. And we get that you get 1.92 times 10 to the negative fifth newtons. Okay. There we go. That's the force on the wire. Okay, so again, electric field and magnetic field isn't a very strong interaction, but you can see it occur. Okay, there is some force there. All right, so let's talk about one more thing really quick. Let's talk about these magnetic field strengths. So you can't calculate the magnetic field strength very well, right? I kind of talked about how to take some calculus calculations and some very high level physics and things like that. But you can measure it, and you actually did measure it with one of those field strength meters. Okay, but how do those things work? Okay, how do you get a device that measures field strength? Okay, well, if you think about it, let's think about one of these problems we were doing, right? How we were sending an electron through a magnetic field and then determining the amount of force it was going to feel, right? So we did this with the right-hand rule just a second ago, right? If an electron is going to the right and goes to the magnetic field, it'll be pushed down with a force going down, okay? And because it's an electron, it goes down because it's a negative, so it'd be left hand, okay? So right-hand rule for positive charges, left-hand rule for negative charges. So the point is, if you could determine how much force is acting on these charges as they move through the magnetic fields, you could determine the magnetic field strength. And so what they do is they make sure the magnetic field is big enough and strong enough that this actually forces it into a circle, okay? If we were continuing that drawing, okay, eventually if you had a big enough field, it would go into like a big loop, basically, and come back on itself, okay? And then using how big the loop is and using kind of the uniform circular motion that we talked about a while back with gravity, you could use the radius to determine how strong the magnetic field is. Okay, so what they make is what they call cyclotrons or Tesla traps. Okay, and so a cyclotron, basically you put a magnetic field through, and then you kind of put a special gas in there that lights up as the electron passes through, and you can determine from the radius how strong the magnetic field is. Okay, and so that's how they measure magnetic fields. Basically, they look at where the electrons are circling, or sometimes they have sensors that see where they hit, and they can determine how much it's bending. Okay, the ones you use for Vernier do that. They look at where the electron would hit on the side. Okay, and use that sensor to determine the field strength, or determine the force, to determine the field strength, and all that stuff. Okay, but it's a really cool way of measuring magnetic fields indirectly by putting charges through, seeing their velocities, and determining the radius to determine how much force must have been applied. Okay, so they're really cool looking devices. Here's another one. It's called a Teltron tube. Okay, but same idea. You can kind of see how much of a radius it has, and you can use that to determine the magnetic field strength. Okay, but there we go. That is magnetism in a nutshell. Okay, again, there's a whole lot of things we're not covering because it takes a lot of higher level math that we haven't covered yet. But really cool stuff. Make sure to do the assignment on the magnetism practice. But let me know if you have any questions, and thank you for watching.